Still circling. It says I'm live. Excellent. Today's the 15th. It's payday. It's payday. Yeah. Stop faking. Anyway, ladies and gentlemen. I'm already in my own head. Ladies and gentlemen, we're going to be doing a deep dive back into quadratics today. I know, right? Now, there is a quizzes assignment already on Google Classroom for you. That is due tomorrow, I believe. That's just a quadratic check that I wanted you to get done. I am currently working through your projects. It's going to take me a little bit of time to get through all of them, but I am diligently getting through them all, as I have other majors to grade for other classes as well. And I want to get you appropriate feedback when the time is there. A reminder to you all about tomorrow with the virtual meetings. Virtual meetings tomorrow are going to be slightly altered in terms of times. I'm going to post a JPEG just to make it very simple. Here's the time, blah, 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 and we'll get there. And then, oh, so happy day. Time is going to be flying by like you wouldn't believe. And then we got 2 weeks, and then we got the week off. I'm going to be live streaming November 3rd on my personal channel. It's going to be great. I'm going to be live streaming and have all my predictions. I'm going to update that thing in real time. It's going to be phenomenal. I just like numbers. Just saying. It's going to be a fun time. I don't know how late we're staying up for, but we'll stay up. Oh my gosh, what a noise. Y'all hear that? Y'all hear that in the live stream? It was like an elk. Oh my word. What, just be an elk?
Not just like go there.
I think they would shoot you. Anyway, here's how I want to start this. Hold on. Here's how I want to start this. I want to go to Desmos. Oh no. I want to go to Desmos. And I want to show you something on Desmos just to kind of give you a recap as to what happened last week and where we're going to be going this week. As I said, it's going to be a little bit of a deep dive. And the reason why it's a deep dive is because we're diving into another dimension. It's amazing. No. You'll see. So, for example, last week I might give you a quadratic that looks like that. And I would say something to the effect of, hey, solve that quadratic. And if I said solve that quadratic, oh, he's asking if a week off. It's the first week in November. But anyway, back to this. If you had to solve this quadratic, solving a quadratic means that you are finding the solutions, the roots, the zeros, the x-intercepts. But then the problem was, what's the deal with the x-intercepts of this graph? Where are the x-intercepts of this graph? They're nowhere. Last week, we would have answered this question, no real solutions. That's how we would have answered this question last week. No real solutions. This week, we can't do that. This week, we have to go a bit deeper. We cannot answer no real solutions. In the 1800s, there was a mathematician by the name of Carl Gauss, amazing fellow. A lot of anecdotes about him when he was a child, outsmarting his teacher with advanced calculus and things of that nature that he was able to teach himself at age 12. But Carl Gauss spent a lot of time in another dimension of numbers. Now, I'm going to show you a video kind of introducing this, but I want to get your mindset right here. When you were a kid and you first started counting, you would go like 1, 2, 3, 4, blah, 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 blah. Those numbers are your counting numbers. They are your what we call natural numbers. But then we discovered numbers on the other side of the number line. What are the numbers on the other side of the number line? The negative numbers. Now, that encompassed a whole new group of numbers that we called integers. Okay, but we called them integers. Integers now included negative numbers and zero. In fact, I could probably draw a visual of this once I get the right marker. Nah, I'll use this marker. Here we go. I'll show you a visual of what I'm referring to. So like 1, 2, 3, etc. They're called the natural numbers, and they existed in their own little bubble. And then the bubble expanded a little bit more, and now all of a sudden we have negative numbers. We also have zero. We called these the integers, but then our bubble expanded more. And when our bubble expanded more, that's when we had fractions. Fractions, now, we didn't really call them a designation of fractions. We called them rational numbers. Do you know why we called them rational? What's the root word in rational? Nope. Nope. Ratio. It's just ratio. A ratio, 1 to 2, 2 to 3, 3 to 4. We have fractions now. But now rational numbers included integers, included natural numbers, because you could take the natural number 3 and turn it into a fraction, 3 over 1. Cool. Then we expanded our bubble even more, and we included numbers that we referred to as irrational numbers. But no, I can't call them irrational numbers. We called them real. And this included numbers like the square root of 2 and pi. And now here's what I need you to recognize. Everything within this bubble, everything within all these circles are considered to be what we call real numbers. And when you had to solve a quadratic like this, you eventually got to a point where you would answer no real solution. But the thing is, Carl Gauss, our little mathematical genius, discovered something where he knew that this equation had to have 2 solutions. It has to have 2 solutions. But those 2 solutions are no longer considered to be quote unquote real. Now, when I say what's the opposite of real, people would typically say what? What would they say? What's the opposite of real? Fake. They use the word imaginary. Now, imaginary is it's not the word that I would call it. No, I'm going to call them complex numbers. I'm going to call them complex numbers. Do you know how the Kardashians first came to fame? No, before that.
He was a Olympic guy.
No, that's not the Kardashians. That's Jenner. How did the Kardashians first came to fame?
Reality.
Nope, before that. The dad of the family that eventually the mom divorced, the dad of the family was one of the lawyers for O.J. Simpson during the 90s.
Bruce?
No,
Bruce is not their dad?
he's not their real dad.
What?
How do you not pay attention to these things? I have a video to show you.
I don't really care about them. That's what?
You should still know your history. Back to here, ladies and gentlemen.
f of x
No, it has to do with O.J. Simpson.
equal to x squared plus 1.
Back to this.
We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. a name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
Which I'm not going to make. This guy expects you to read this. I'm not going to expect you to read this. I'm just going to skip ahead.
Missing dimension.
There you go. It's the end of the thing.
So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary.
Now, lateral never stuck. The name that did stick was complex.
To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
That's the end of the video. Now, it's interesting. If I go to my son's in first grade. What's up?
I was gonna say there's an app that I used last year that's like 3D geometry or something like that.
Mhm.
I thought it was really cool because like it's real life and it's through your phone, like you plot the points and like it'll show the thing.
Yeah, and that's the thing. It's really interesting to take a step aside. When you learn geometry last year, you mainly stick to flat geometry. Mainly, you do some 3D stuff, but you mainly stick to flat geometry. But we don't live in a flat world. For example, you know that how many degrees are there inside of a triangle? 180 degrees. That only happens in flat worlds. If you were living in the real world, now imagine this for a moment. Imagine that this is the globe right here, right? And here is the globe, whatever. And then here's the North Pole, right? A straight line from the North Pole down to the equator. A straight line from the North Pole down to the equator, there's 90 degrees. And then another straight line from the North Pole down to the equator, 90 degrees. Now, if I connect these, that would be a triangle. But a triangle that has two 90-degree angles and a third angle that is clearly not 0, more than 180. It's really messed up. Happens in like concave and convex geometry. But the thing is, you have to learn how to crawl before you walk. They teach you basic geometry and problem-solving skills in order to build up to higher things. For example, my son's in first grade. If I go to my son and I say, you're holding 2 apples, I'm going to take away 3, that doesn't make any sense to him. That doesn't make any sense to him. We put problems in a context that they can understand, and then eventually we build them up to higher level concepts. Did you know that the number 0 wasn't widely accepted in mathematics until maybe only 500 years ago? People just didn't know how to deal with it. Think of Roman numerals. You're familiar with Roman numerals? What's the Roman numeral for 0? There is none. Yeah. We have placeholders in our system. We have placeholders. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And when we say 10, we go 1, 0. In the Roman numeral system, they didn't go 1, 0. They went X, and they created a brand new symbol for it. Same thing with 100. It was C. Same thing with 500. I believe it was D. You know your Roman numerals? Yeah. No. Yeah. What's really weird is if you see a clock with Roman numerals around the side, a lot of the time it'll go 3 and then 4, and then the 4 will be an IV. But the traditional way that it really should be is like I. You'll see that on some clocks. Anyway, back to this.
Yeah, because the IV is like it's -4.
I know. It's funny because my kid's in first grade. He doesn't like math, but he was doing his math homework the other day, and they're doing math homework like adding numbers and getting 2-digit answers. Did I tell you this story? He's getting 2-digit answers. That's what I told you? It's fantastic. It really was. I told that to a few classes, and like some of them are like, wow, I just got shown up by a first grader. Because like, yeah, 8 plus 7. How'd you get it? He's like, well, I saw 7 plus 7. I'm like, what a smart kid. He prefers art. He prefers ILA. See, the thing is, people are afraid of what they don't understand. And for the longest time, people did not understand negative numbers. And then eventually, people realized the practical. People did not understand fractions. People didn't understand square roots, for example. For example, check this out. You do this example in geometry last year, where you have a right angle triangle, and you have like a side of 1 and a side of 1. And you guys are taught to do the Pythagorean theorem, where you go 1 squared plus 1 squared equals c squared. That's c squared equals 2. And then this side should be the square root of 2, right? Here's the thing. There is no fraction. There's no fraction that you can say equals the square root of 2. There's no way to write it as a fraction. That's why they call it an irrational number. The Pythagoreans, who were a cult, I don't know if anyone told you this, they were a cult. They found this out, that they couldn't write it as a fraction, and they were so afraid that the world would find out that they didn't know the answer, that they basically swore everyone to secrecy, saying, don't tell anyone about this. People who did were killed. About the fact that you can't write that as a fraction. You can't come up with a fraction where A and B are not real numbers, but integers, and get the square root of 2. You can't. There's no possible way. Can't do it. You can get as close as possible, but you'll never get there. We're afraid of what we don't understand. Now, the thing is, I'm about to show applications to quadratics for imaginary numbers and complex numbers. But in reality, if you want real world application, you really have to go towards an engineering field. If you have any type of a desire to go into an engineering field, electrical engineering, biochemical engineering, mechanical engineering, then you're going to see the practical applications of complex numbers. Yes, they did have a cult for math problems, but it was about mathematical knowledge. In fact, the Pythagoreans, again, very strict cult. Fun fact, the Pythagoreans were the first people in history to discover the mathematical principles of octaves. Do you know what octaves are? Musical octaves. He's nodding his head yes. The idea that like I could hit a C note, and then I can go up an octave and hit a C note again, but it sounds different because one's higher or lower than the other, but it's still a C note. The Pythagoreans were the first ones to discover that principle. Anyway, ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out. and open. I want to teach a class called The History of Math. I really do. There's so many stories about mathematics. Let me tell you one right now. You know the Nobel Prize? The Nobel Prizes, right? The Nobel Peace Prize, the Nobel Prize for Physics, the Nobel Prize for Economics. Did you know that there's no Nobel Prize for mathematics? None. No such thing. Alfred Nobel, the guy who originally left the funding to actually do the Nobel Prizes in the first place, decreed that there would not be a Nobel Prize for mathematics. The reason why? He did not like mathematicians because one slept with his wife. That's a true story. Let's call this quadratic formula continued. Today is the 15th. See, these are the stories that they don't actually tell you. Is he okay? Does he have a headache? Oh no, you got a notebook? There he goes. First, let's talk about the square root of -1. I'll just kind of introduce it like that. You guys for years have been told, I know square roots. I know how to do square roots. What's the square root of 81? It's 9. Why is it 9? But why? Because 9 times 9. What's the square root of 144? 12. Why? Because 12 times 12. Square root of 4 is 2 because of 2 times 2. I'm okay. But what is the square root of -1? Because you could, if you guess maybe, oh, well, the answer could be 1. It can't be because 1 times 1 is not -1. Oh, maybe the answer is -1. Sorry, can't do that either because -1 times -1 is positive. This was a number for so long that eluded mathematicians. The square root of -1 is a number. But remember all those bubbles that I drew earlier, those rings? It doesn't fit into any of them. This is not what we would deem to be a real number. It's not a counting number. It's not a fraction. It's not irrational. It's not rational. It can't do any of that stuff. But it still exists. It just exists in another dimensional plane. See, the thing is, mathematicians were able to describe this number mathematically. They're able to do calculations with this number. They're able to do a lot of stuff with this number, but it's difficult to actually show what this number actually is. So, in order to make things simple, mathematicians denoted that this number would be written as an I, which is where that term imaginary originally derived from, I should say. It does look like a backwards J, but no, it's really an I. Let me show you what I mean. Believe it or not, I has been staring you in the face for years. Did you know that? It's not pi. Look right here. You see that decimal point? It's going to focus in a moment. Look what's written above that decimal point in yellow. There it is. It's been staring you in the face for years. For now and forever, whenever you see the square root of -1, you can replace it with the symbol I, which is now what we will call a complex number. The example being something like the square root of -9. Which normally we can't calculate the square root of -9 because the square root of -9 is not a real answer. And I'm going to show you this on the calculator in a moment. It's not a real number. But thanks to geometry and what you guys did with simplifying radicals, you remember that last year? I can break this up into the square root of 9 and the square root of -1. Whether you remember it or not, this is what you did in geometry. Like, oh, I have the square root of 50. You can't leave it as the square root of 50, but you can break the 50 up into 25 and 2. I can break up the -9 into 9 and -1 because the square root of 9 is simply 3, and the square root of -1, we will now denote it as an I. We get 3i. It seems strange.
But is it just, it's called a factoring?
We eventually will get to something like that. You'll see. Yeah. But it's like, for example, I'll give you another example here, like the square root of negative 50, for example, right? The square root of negative 50, I can break it up to be the square root of 25, the square root of negative 1, the square root of 2. The only thing that's different between last year and this year is the square root of negative 1. This becomes 5i times the square root of 2. Whenever you see the square root of a negative, you just simply have to take the negative out, and it becomes an I. That's all that happens. That's the only difference between it. On your graphing calculators, if I zoom in here a little bit, on your graphing calculators, if you were to try to take the square root of negative 9, for example, your calculator would say error. No, you can't do this. Watch. Boom. There's the error. But what type of error? What type of error? Non-real answer. Non-real. It's not a real answer. But again, real is kind of the unfortunate name because it exists. It does exist. There is actually a way to change your calculator in the mode down where it says real. You can actually change it to be A plus BI, which changes your calculator to be complex now. So now when you go through those calculations, your calculator would be like, oh, you did want the complex answer. Okay, I'll give you the complex answer. So now when I do the square root of negative 9, boom, 3i. Not messed up. You can change the mode. You can do anything you want. Yeah, calculator can do all sorts of things.
Why don't we learn to use calculators? No one knows how to use calculators.
All that people really think they need are the numbers and the operations. In reality, before the end of the school year, I am going to show you.
They all know like sin x.
Let me get there. Before the end of the school year, I am going to show you how to use the ln and log function over here. If you end up doing trigonometry, you will learn how to do the sine, cosine, tangent functions. And if you end up doing statistics, I will show you what's underneath the stat button and vars button. Go ahead.
In geometry, we use the same code as tangent.
Oh, so you do SOHCAHTOA a little bit.
Yeah, we did. We actually had a lot last year.
Do you end up doing stuff like this? Hold on. Do you end up doing stuff like this? Oh.
Not that, but like we do a lot of stuff.
Yeah, in trigonometry, you're going to see stuff like that. But anyway, I digress. Trying to get into the live stream here. Now, for example, if I did the square root of negative 50 now, it actually won't say what I wrote on paper because the square root of 50 is a decimal. Oh, non-real answer. Sorry, I reset my calculator. There we go. If I do it, it'll give me this decimal, which is really whatever the square root of 50 is, but look what's at the very end of it. I. Because the square root of 50 is just this decimal, but with an I at the end.
So can you just do 7.79?
7.07. You could, but that's not an acceptable answer. See, in mathematics, you would have to do something like this. Oops, sorry. In mathematics, you would have to do something like what I wrote here in order to get a proper answer.
Wait, why not make 7.19?
Because mathematicians don't like decimals. We prefer not to use them. You are in this classroom. So back to this. Now here's something crazy. I squared. I squared is the calculation I times I. A complex number times a complex number. If you were to take I squared, well, what is I? What did we denote I actually is? No, it's not negative 1. Square root of negative 1. I want to be very clear about that because, again, what you just said is a common mistake. When I say, what actually is I? People are like, oh, it's negative 1. No, it's not. It's the square root of negative 1. So if I take I and replace it with the square root of negative 1, look what I have here now. What happens when a square and a square root come into contact with each other? A square and a square root. What happens when you combine addition and subtraction typically? Or they cancel out. What about multiplication, division? They cancel out. Square root and a square, they cancel out, leaving you with -1. I'm going to show you this on the calculator in a moment. I know. You're going to see eventually how easy this can be.
I mean, it seems like there's just a lot.
No, I know. Well, think of it this way. Basically, what I'm trying to show you is this. Your entire life, you've had a certain set of rules that you apply. Like you take you get up from your desk, you walk to the door, you expect that the floor is going to hold you up. You expect that, right? Now, obviously, that's not always the case, but you expect that to happen. But one day, you get up from your desk and you walk to the door, and then you float up to the ceiling. You weren't expecting that, were you? You don't really know what to do now that you're floating up to the ceiling. That's what this is happening right here. Your entire life, you were used to a certain set of rules for mathematics. And now all of a sudden, I'm taking these rules and showing you something that seems insane, but it actually does work. Oh, believe me, it does work. Let me show you what I mean. Here's an example. Example. Solve x squared plus 4 equals 0. Here's the example that I have, and this is where it applies. Now, according to the fundamental theorem of algebra, this thing should have 2 solutions, and it does. It does have 2 solutions. Now, hold on. Let's get there. Now, if I were an Algebra 2 student and I was faced with a problem like this that they told me to solve, the first thing that I would attempt to do would be to factor. I would attempt to factor. So, the b value was not there. The b value was 0. A times c will give me a 4. Can you think of 2 numbers that multiply to 4 and add up to 0? 2 numbers that multiply to 4 and add up to 0. You could say 2 times 2, but that doesn't add up to 0. You could say -2 and -2, but that doesn't add up to 0. You could say, 2 and -2, but that doesn't multiply to 4. No such numbers exist. No, I didn't say that. Last week, I gave you a star in your notes. And I told you that if you can't factor, or if factoring is not going to work, the quadratic formula will always work. So we are going to have to go after the quadratic formula. Here, fill this out while I'm writing something. So, if I'm doing the quadratic formula, I'm going to identify A, B, and C as 1, 0, and 4. Because the B value is not there, you have to assume to be a 0. It's a 1x squared, and the C value is 4. I'm going to calculate my discriminant separately. My discriminant being b squared minus 4ac, which would be a 0 squared minus 4 times 1 times 4, which ultimately gives me a discriminant of -16. Now, if you go back to your notes from last week, something that I declared to you was that if you had a negative discriminant, that implied no real solution. Now, I emphasize the word real. No real solution. So hold on, let me write this little note for myself. Because the discriminant is negative, no real solution. However, now I say however very calmly, but I'm saying however with all capitals. Because your discriminant is negative, there is no real solution. However, there are two complex solutions. There are two complex solutions. So we're actually going to find those in a moment. But I want to emphasize this point. This graph, if I were to put this graph on Desmos, go back to Desmos real quick. If I go back to Desmos and put that thing there, you can see it. You can see it right there. It does not cross the x-axis. There is no x-intercept to speak of. There is no real solution. However, there are two complex solutions. Let's go through the quadratic formula. Negative b plus or minus the square root of the discriminant, the whole thing, divided by 2 times a. Now, that negative 0 is not going to do anything. That negative 0 is just 0. It's just not going to do anything. It just goes away. But we have to evaluate some stuff. Now, the plus or minus is still there. The 2 is still on the bottom. But the square root of 16, or sorry, negative 16. I can break that apart, the square root of negative 16. I can break that apart to be the square root of 16 and the square root of negative 1, based on what we just did earlier. And I can even check this in my calculator. I guarantee you that if I took the square root of negative 16 in my calculator, it would spit out a 4i. Plus or minus 4i over 2, which just simplifies to become plus or minus 2i. There are still two solutions. They just so happen to be complex. These two solutions, positive 2i and negative 2i. How do you check to make sure that you're right, typically? Put it back into the problem. And if it's a true statement, it works. Yeah, let's try it. Now remember, 2 doesn't work. 2 squared is 4. 4 plus 4 is 8. Doesn't work. Negative 2 doesn't work. Negative 2 squared is 4. Plus 4 is 0. I'm sorry, 8. 2 and negative 2 are not going to work, but that's not what we got. We got 2i and negative 2i. Now check this out. If I were, I'll use this marker. Here we go. If I were to take this and plug in a 2i, I have to think to myself, well, what is 2i times 2i? What is 2i times 2i? Well, first of all, 2 times 2.
Oh, 4.
Yay, we did it. 2 times 2 is 4, but then what's I times I? I squared, which I did say what I squared was. So hold on, this would be 4i squared, which is actually 4 times what? Negative 1. It's negative 1. I squared is negative 1. We wrote this into our notes earlier. I squared is actually equal to negative 1. I'll show you that in the calculator. This is negative 1, which equals negative 4. 2i squared is actually negative 4. And then negative 4 plus 4 is 0. This is really messed up. I'm basically saying, hey, you're floating to the ceiling. Figure it out. Let's look what the calculator says. Let me zoom in a bit. Let's look what the calculator says. Now, first of all, on the calculator, I squared, you could see it right there, I squared. I squared is indeed negative 1. That's what I squared is. That's the reason that it exists. And then if I were to take 2i, notice the parentheses, squared plus 4, that would be the plugging back in that you were referring to because it's x squared plus 4. But if I were to take 2i parentheses squared plus 4, if I'm correct, it's a 0. Because of this fact, 2i squared by itself is just -4. -4 plus 4 is 0. It's so messed up. It is so messed up. I'm basically trying to get you to think in a dimension that you're not used to. You guys ever hear of the book Flatland? Did I tell you about that? I'll ask him when he comes in. Well, I have a question for you. You ever hear of the book called Flatland? Flatland is an amazing book. It describes a world in which all the creatures that live in this world are two-dimensional. They're flat. They only see each other in 2 dimensions. So if you were a triangle, for example, no one would actually know that your shape was a triangle because you would be lying flat on the ground and people would be looking at you flat on the ground. They wouldn't be able to tell. The only way you'd be able to tell that you were a triangle is if you were a 3-dimensional creature that existed outside of their universe. Well, you could potentially measure the sides, That's also a possibility. You know. So now imagine this for a moment. Imagine that you are a creature living in this flat world. And then all of a sudden, a ball enters your world, a 3-dimensional ball. No, it exists. But it exists first as a singular point. And then it expands. And then you're like, what is this? And then all of a sudden, as the ball leaves your world, the disc kind of becomes smaller and smaller and smaller to the point where it disappears. And then you're like, what the heck was that? Because you have no concept as to what a 3-dimensional ball actually is. The only thing that you can see at any given point is, boom, there's a point that just showed up and expanded and then disappeared. Our brains can't, if we lived in that 2D world, our brains couldn't handle it. Yeah. I just told you, if we lived in a 2-dimensional flat world, the only thing that we would see was that little spot. The thing is, we can't think outside of the dimension that we're in. Now, we live in a 3-dimensional world. Now, imagine a 4th-dimensional object entered our world and then left our world. That's a good question. Again, how do we have any concept for it? It's called a tesseract, and it's not the 5th dimension. It demonstrates the 4th dimension. It's a 3D projection of a 4th-dimensional object. It is really neat, but again, our brains can't handle it and fully understand what's going on with it because we live in a 3-dimensional world. Now, what I'm trying to show you is another dimension to numbers. The fact that there is another dimension to numbers is vitally important. Here, you got to copy these down. That's the page that you missed. Let's try this problem. Now, this is a problem that I introduced last week. It's a problem that I introduced last week. It's a problem that I put on the board today, and it's a problem that I would like to solve using the quad formula. Now, as we've done always with the quad formula, we begin with the discriminant. You begin with the value of the discriminant. I was trying to write the word discriminant for a second. No, I want to write b squared minus 4ac. The value of a, b, and c are all 1. So I'm going to go through this. 1 squared minus 4 times 1 times 1. If you did that correctly, you should be getting a discriminant of -3. Now, again, last week, we would have answered no real solution. This week, we can't do that. So I got to go a little bit farther. Let's go to the quad formula. -b plus or minus the square root of the discriminant, the whole thing, over 2 times a, which is 2 times 1 in this case. Ooh. What did I tell you was going to happen when you take the square root of a negative? What is supposed to rear its ugly head if you take the square root of a negative? A complex number, which we're going to denote as, what do we use to denote a complex number? what symbol or character do we typically say is a complex number?
Oh, I.
Just I. So check this out. Here's how I'm going to have you go about this. It's actually, honestly, if you look at it the right way, the easiest thing in the world. Watch. -1 plus or minus I root 3 over 2. Thank you.
That's the answer.
Yes. That.
You're putting the I.
Yes. You take the, now check this out. I'll show you. I know. Like I said, if you look at it the right way, it's quite possibly the easiest thing in the world. See, because the thing is, now you can continue. Okay, can I simplify the square root of 3 any farther? We'll deal with that. But check this junk out. Check this junk out. What ends up happening is the square root of -3 is just simply put the square root of 3 times the square root of -1. And we know that the square root of -1 is just going to become an I. We typically write the I before the square root. We typically write the I before the square root because we don't want people to be confused as to whether or not the I is under or not under the radical. Whenever you see the square root of a negative, you can just simply take it out just like that. And as long as you take it out just like that, you're fine. You're golden. Phenomenal. Amazing. I know. But that's how we get both our answers. Now check this junk out. Check this junk out. Watch this. We said before, how do we check to make sure we're right? Well, I'm about to show you. Now, in this case, here's x squared plus x plus 1. Now, obviously, here's the graph on the graphing calculator. There it is. Boom. No real solution. No real solution. Okay, we expected that. But now, I want to see if we're right or not. So I'm going to take the function, and I'm going to plug in the answer that we believe we got. -1 plus I root 3 divided by 2. What I'm basically doing is I'm taking that number that we found with I, and I am plugging it in to that function. And if I am correct, what should happen? No, that's not what I said. If you now, keep in mind, you were actually out of the room for half a second. I asked the question before, how do we know we're right? How do we typically check to make sure we're right? She said we usually plug the answer back in to see if we're right. This is what I'm doing. I'm taking the answer that we found and I'm plugging it back into this function up top. If I'm correct, what should happen when I hit enter? Boo! Ah, what happened there? Data type? Hold on. That opened that. That opened that. Divided by 0. Boom. Ah, data type. Let's try it like this then. Ready? Check this out. -1 plus plus I, the square root of 3, close, divided by 2 squared plus -1 plus I, the square root of 3, divided by 2, plus 1. This should work. I don't know. There it is. Now let me change it up. Let me change those pluses to minuses. Boom. Boom. There's another 0. I don't know. My brain works in like chunks. It's like, you know how people typically read like a page top to bottom, left to right? That's not how my mind works. I'm not really sure how it works. Let's try this. 11:05. I got time. Let me show you another one. Ladies and gentlemen, this is a problem off of that worksheet that we did last week. Instead of actually jumping to that worksheet, let me just write down the problem for you. This is problem number 26 from the worksheet from last week. It is the problem x squared plus 3x plus 6 equals 0, and they tell you to solve. Now, because of everything that we've done today and last week, you have all the tools you need. Because of everything that we've done with factoring, because of everything that we've done with quad formula, and because of everything that we've done with I, you now have all the tools you need. So I look at this problem and I am going to try to solve this. Let's say I want to try to solve by factoring. What's A times C for this problem? Okay, two numbers that multiply to 6 and add up to 3. Can't do it. So what do you rely on? I'm not at I yet. I only have to worry about I if I'm taking the square root of a negative. If factoring doesn't work, what do you do?
The quad formula.
Quad formula.
4 equals 4 minus AC.
No. The discriminant is b squared minus 4ac. We need to have that formula memorized, though. We need to have that formula memorized because obviously if you are off by a tiny bit, then the whole thing's going to fall apart. 3 squared minus 4 times 1 times 6. If you did that correctly, you should be getting a negative 15. 9 minus 24. Now again, just to walk through the process, if you were doing a problem like this, this would mean no real solution. But it also means two complex solutions. I want to emphasize something. Whether it be the SATs or state tests or an assessment in my class, it doesn't matter. You always have to pay attention to the directions. Sometimes the directions will say, hey, find me the x-intercepts. Oh, but what if there are no x-intercepts? Well, then you would say there's no x-intercept, there's no solution. If the problem said, find me the real solutions, then at this point, if the problem said to find me the real solutions, you would say that there are no real solutions. But if the problem just said to solve, or find the roots, or whatever it's asking in that sense, you got to go farther. Well, I'm going to keep going through the quad formula. The complex solution will show up when I take the square root of a negative.
So how do you know that there's 2 complex solutions?
Well, last week, when we discovered the discriminant, if the discriminant was positive, I said to write down 2 real solutions. If it was 0, there was 1 real solution. If it was negative, you would say no real solution. But according to the video that we watched today, even if there are no real solutions, there should always be 2 solutions, but they are no longer real. They live in the complex world, a world that we are still trying to wrap our heads around. Negative b plus or minus the square root of the discriminant, the whole thing, over 2 times a. This becomes negative 3. Now, this is where the magic comes into play. Square root of a negative. Done.
So you keep putting the I in front of it?
Correct. If you take the square root of a negative. Now, the thing is, can you simplify the square root of 15 any farther? What does 15 break up into? Well, a decimal, about like 3 and 5, maybe.
Oh,
Yeah, that's what I'm saying. For example, now, if you ended up with like the square root of 48, for example, that's not a whole number, that's a decimal, but you can split that up to be root 16, root 3, or 4, root 3. If that's what you had, that's what you got to do.
so if it's positive, you write down that. If it's negative, you put the I.
Well, check this out. You ready for this?
Yeah, that's what I was thinking. Right now, there's
That's the only difference. Hold one second.
Good morning. I just want to let
crap.
everybody know, at exactly 11 o'clock, we will be doing a fire drill. This fire drill, we will not evacuate the building. We will not.
Let the man talk.
We will pull the alarm at exactly 11 o'clock. Briefly, will sound. Teachers, please just explain where you would go and what you would do in case of an actual fire. Again, we will not evacuate the building when the fire alarm sounds. Please stay in your classrooms. We'll be very brief.
Yes.
Thank you, everyone.
Okay, give me 1 second. I'll answer your question in one moment. Okay, I'm going to explain that as well. Don't worry. Now listen, with the time that we had, my hope was to get to a few more problems on this thing, but I have to be off the live stream at 11 because they're going to be doing the fire drill. You know. Well, I know. Go ahead.
We're gonna apply the river thing inside.
Correct.
Why?
Wonderful, right?
I hate this school.
I don't have an answer for you. It's again, it irks me when people say I hate this school because it's every school in America. It's not just our school. Everybody thinks the grass is greener on the other side. Everybody thinks their life would be better if they went to a different school in the county. But the reality is we're just like every other school. So knock it off. Next. When it comes, hold on. I'm going to answer the question about the square root of negative 48 in a moment because I do have a couple of minutes. But here's going to be my thing. Because the time that I lost because of this whole fire drill thing, I wasn't able to get through the last couple of problems that I did. Something similar happened on Monday, not with the fire drill, but just running out of time. So what I'm going to do is I'm going to do something that was going to do for the Monday kids as well. I'm going to make a video in regards to a word problem that's on here and a couple of extra problems that I would like to do. And I'm going to have that video posted for tomorrow. So please don't worry about that. Next, answering this question right here. I'm going to do this over again. In geometry, maybe you were faced with a problem. Now, mind you, this is also going to hopefully answer your question about negative 48. I'm just going to do a different number. I had the square root of 20. Now, 20 is not a perfect square, right? But you can't leave it like that. So in geometry, what you were taught, or what I hope you were taught, was the fact that you could break this thing up. That's a 5. You could break this thing up where one of those numbers is the largest possible perfect square. And then this becomes 2 root 5, and that would be what they called simplified. Again, that's something that you learned last year with Pythagorean theorem and junk like that. But now what I'm saying, because with the negative, check this out, if you were taking the square root of negative 20, that negative is still there. Exactly, which would become that I. Because of the square root of negative 4, the square root of negative 4 would have to become 2I, because anytime you take the square root of a negative, I is going to rear its ugly head. Exactly. If you wanted to do it that way, it would be this. And then it would be 2I root 5. Exactly. Now, again, I do apologize for the lack of time because I know you're asking that question about the 48. Like I said, I am going to make a video that I'm going to post tomorrow specifically for our virtual meetings because I do have to be off of the live stream when they do the fire drill. So I do apologize. I'm going to have to click off of it now. But tune in tomorrow and we'll do this thing. Boom. Now, to answer your question about